Question 9. The diagram shows two vertical posts, AB and CD, on a horizontal ground. It tells us the ratio between CD and AB is 1.5 to 1. So we'll write that down first. And I'm going to write this as 3 over 2 to 1. And it says that AB is 1.7 metres. So if AB is 1.7 metres, then CD is 3 over 2 or 1.5 times bigger. So on your calculator you can do 1.7 times 1.5 or 1.7 times 3 divided by 2 to work out what CD actually is. So I'll do that on my calculator now. So I will have 1.7 times 1.5, and that gives 2.55 metres. So I can put that on my diagram. It says the angle of elevation of C from A, so from here looking up to there, so I'll just change that a little to make it a bit more neat. So of C from A, okay, so that's where we're looking at C from A. So that's the elevation, and the angle of elevation is from the horizontal. So we know that this angle here is 52 degrees. So the nice thing is we can work this length out here. It's 2.55 minus 1.7, which is 0.85 metres. And then we've got a nice right angle triangle here because this is the horizontal. So in this right angle triangle we've got the angle here, we've got the opposite, and we've got to work out BD, which is the adjacent. So if we've got the opposite and the adjacent, then without going into too much detail of the trigonometry, then it's this one we want. Tan is opposite over adjacent. So I'll give myself a bit of room here. And I'll change the colour. So opposite and adjacent. So tan of 52 is 0.85 divided by the adjacent, which is what we want, which is BD. So if we times both sides by A and divide both sides by tan 52, we'll get the answer. If you don't like that, then what you can do is you can invert both sides or find the reciprocal of both sides. So that means 1 over tan 52 is A over 0.85, and then you can times both sides by 0.85, and so A would be 0.85 divided by tan 52 in degrees, and you can use your calculator for that. So 0.85 divided by tan 52, make sure it's in degrees, and what I get is, I'll get BD, and I'll write down my calculator display first. And now I'm going to do it to 3 significant figures. So BD is going to be 0.664 metres to 3 significant figures. Question 10. On the grid, shade the region that satisfies all these inequalities. Now, my favourite way of doing these is to draw them as straight lines first, i.e. don't look at the inequalities. So just have y equals 3x here, have y equals x minus 1 here, and then get this as y equals, and you'd have y equals minus x plus 4, because you'd take x from both sides. And so what I'm going to do is I'm just going to graph each of these in turn. So let's have a look at the first one, y equals 3x. So that has an intercept of 0 and a gradient of 3. So we should be able to plot those points. So an intercept of 0 means it must go through the origin, and that means for every one I go along it goes up by 3. So we can just plot these points here, and then along 1 and up 3 again, along 1 and up 3, and we can also go along back 1 and down 3, and so on and so forth. So I'll plot that one first. So that would be y equals 3x. And then I'm going to do this one, y equals x minus 1. Well, this has an intercept of minus 1, so it cuts there, and a gradient of 1. So for every one I go along, I go up by 1. So along 1, up 1, along 1, up 1, and so on. And I just draw a line through there, so I can do that now. And then lastly, I can do the line y equals negative x plus 4. So it has an intercept of 4 and a gradient of negative 1, so it's going downhill. So for every one I go along, I should go down by 1. So it cuts through there, along 1, down 1, and so on. So I can do a line going through those points. And there's our 3 lines, but we want inequalities here. So let's have a look really carefully at what we have. So for this one, we have y is less than 3x. So we've got to do everything underneath that line and not equal to. So it's definitely going to be a dotted line because it's not equal to. In fact, all of them are going to be dotted, so we can do that now. And you would just do that in the exam in pencil, obviously. And so we can do that. And so we want everything less than that, so I'm going to change the colours here. What colour should we have? Let's have green. And everything less than that, so I'm just going to shade that in here. And then we want to look at, say, this one, and that is greater than, so everything more than the line x minus 1. Well, there's the line x minus 1. We want everything more than this, so I'll change the shading here to yellow, and we want everything more than this, so there we go. You can probably see already it's going to be this region here, but if you can't, then the last one is we want less than again, so let's change the colour, and we want everything less than this line here. Now I'm sure you can notice now that the only region that is shaded in all 3 times is this region here, and you would just shade that in, and that would be your answer. And you've got to label it R, and there we go. Okay, so that's the best advice I can give on this type of question. If you know your straight lines reasonably well, then you should have no problem at all. Question 11. We've got to write this expression here, x squared plus 2x minus 8, in this particular form here, where m and n are integers. Well, that's really along the lines of completing the square. And when we complete a square, we do exactly that. We complete and make a square. And the general basis of this is we always have x in here, we always follow this sign, and we always halve this number. And we have a look at what x plus 1 multiplied by itself would actually be. And you can do this in your head perhaps, but we can use a grid if not. And you'd get x squared, which is good, that's what we wanted. We've got 2x here, which is what we wanted. But we didn't really have a 1 here, did we? So if we take that 1 away, then this has to be exactly the same as this. And then we just write the minus 8 here because we didn't touch that at all. So our final answer should be x plus 1 all squared minus 9. So m in this case would be 1 and n would be negative 9. Now if you want to look at some more videos on completing the square, then I have a couple in some of the playlists under algebra. but so do many other people, so have a little look at those if you're still not sure. Question 12. What we have to do here is work out the volume of the cuboid. And we're given that AB is 7 centimetres here. AF is 5. And what else we're given is the fact that FC is 15. And that's that dotted diagonal here. So having looked at this for the first time, I think what I would do is I would imagine that there's a right angle triangle here. There we go. And I know 2 of its lengths, so you've got a calculator. You can work out that AC squared must be FC squared, which is 15 squared, the hypotenuse, minus one of the shorter sides squared, 5 squared. And that's 225 minus 25, which is 200. So AC is the square root of 200, and that's the same as the square root of 100 times the square root of 2, which is 10 root 2, and you might have a decimal, so you can just use that if you want. Now, that helps me find AC, which is this length here. Now I've got another right angle triangle here, and I know 2 of those lengths, so I can now find BC. I'll use a different colour here. So BC squared is going to be AC squared, which I already had here, which is just 200. And then let's have a look. So BC squared will be 200 squared, and that'll be minus 7 squared. Okay, because we've got one of the shorter sides we want to find. So we've got 200 minus 49, which is 151. So BC is the square root of 151. So how do we use that to find the volume? Well, it's quite nice now, because to find the volume we just needed this length by this length by this one. Okay, so we've got the volume is going to be 5 times 7 times one of the other dimensions, which is BC, which is root 151. So that's 35 root 151. And then I'm finally going to use my calculator now. You've probably used yours before. It's sometimes good practice for surds to not use the calculator when you're practicing these papers. So 35 times 151 to the power 0.5 I shall do. And that gives me a volume. I'm going to do it to 3 significant figures. I got 430.0872005, but to 3 significant figures that's going to be 430, and it's going to be in centimetre cubes, and I'm just going to write 3SF there. Question 13. There are 14 boys and 12 girls in a class, and you've got to work out the total number of ways that one boy and one girl can be chosen from the class. I don't like this question, having just seen it, but I'll try and we'll see. It's probably really easy. I'm going to label these B1, B2, B3 and so on, up to B14 for the boys, and then G1, G2, G3 up to G12 for the girls. And I think it's a matter of saying, if you pick this first boy here, then you can either pick this girl or any of the other 12. So for the first one, for the first boy, there are 12 ways of picking the next girl, because you can pick any of the girls. And then for the second boy, it must be the same again. For the second boy, you can either have this girl, this one, up to the 12th one. So I think for each of the 14 boys, there are 12 girls to choose from. And so you've got 14 times 12, which is 168 ways. Now you could argue that, and I'll change the colour here, you could argue that you could start with this girl here and reverse the process and say for each of the 12 girls there are 14 boys to choose from, and therefore double this number. But if we're looking at choosing that particular boy and that particular girl as an outcome, then the order GB or BG doesn't particularly matter. So I would stick with 168 unique ways. Question 14. We've got a very difficult expression here, and we must write it as a single fraction in its simplest form. So let's start by writing it out. Now, the first thing that I would do is I would look at this part here and I would factorise that. So we've got x plus 3 divided by, and then we've got x, and then another x, and then we've got 3 and 2 and both plus. Because that would then give us our x squared, 2x, and 3x is the 5x, and then 3 times the 2 gives the 6. The next thing to look at would be this division sign here. You should know that if you're dividing a fraction, it's the same as timesing the inverse or the reciprocal. So if I write down what I mean, so this becomes times, and then the denominator becomes the numerator, and the numerator becomes the denominator. And you can just test that out with simple numbers. So if you wanted to try, for example, 3/4 divided by 2/3, well, that's exactly the same as 3/4 times 3/2. Okay, so I won't go into massive detail now, but that's one thing that you can actually do. So in this case, what I have here, if you think about it, is a fraction multiplied by a fraction. Now, hopefully you can see here that x plus 3 divided by x plus 3 is 1, so that would cancel. And so you're left with 4 minus x minus 2 divided by x plus 2. Create a little bit more room here. That's the same as and then what I can do is create a common denominator by timesing this up by x plus 2, top and bottom. And then I've got a common denominator of x plus 2, and then on top I have 4x plus 8, that's just multiplying this part out, minus x plus 2. That's really important. So that's going to give me 3x plus 10 divided by x plus 2. Question 15. It says a virus on a computer is causing errors, and an antivirus program is run to remove these errors. Now it says an estimate for the number of errors at the end of t hours is 10 to the 6, which is 1,000,000, times 2 to the minus t. And I'd rather write that as 10 to the 6 times 1 over 2 to the t. Now part A says work out an estimate. Now reading that, it says the word estimate twice, so I don't think it means, say for example, t is 8 hours. I don't think it's saying work out an estimate for 1,000,000 divided by, well, 2 to the power 8 you can do on your calculator, which is 256. I don't think it's then saying do 1,000,000 divided by, say, 250, and you'd get 4,000. I don't think it's saying that. I think what the question is saying, although I'm not too sure myself, but try and trust me on this one, I think what it's saying is because this formula was an estimate in the first place, just use that formula. So not a brilliantly worded question in my opinion. It's a bit confusing. So what we're going to do on our calculator is exactly what it says here, and that is 10 to the power 6 divided by 256. So let's see what we get. So 10 to the power 6, which is 10 times by itself 6 times, divided by 256, and I'll write down what I've got on my calculator. And to be honest, I would probably just write that. If you want to round it to the nearest whole one and put 3,906, I'm sure that would be fine, but I'm just going to leave that. It's worth 2 marks, and we've done by far enough for 2 marks, that's fine. It then says, explain whether the number of errors on this computer ever reaches 0. Well, this is why I thought ahead and wrote it in this way. Because if you've got a very large number like 1,000,000, and you're multiplying it by a number which is, say, 1 divided by something which gets bigger and bigger and bigger, let's just have a look at what happens to this. Well, if t starts to grow, say t is 3, you'll have 1 over 2 to the power 3, which is 8. And that means you'll have 1/8 of a million, whatever that actually is, 125,000. And then if t grows even more, say when we had 8, we've got 1 divided by 256, which we had in the initial question. So that means you'd have 1/256 of 1,000,000, which is less, but will it ever reach 0? And I would say no, it won't, because even if t is really, really, really large, say 100, 2 to the power 100 is something, and if we're doing 1 divided by 2 to the power 100, that'll be very, very, very small. It could be 1 over something huge, say, I don't know, 100 million or something, but 100 millionth of a million is still something, okay? So it's never going to reach 0. So we would say never going to reach 0, and I would say because, and you can write because like that, 1 over 2t is never 0 itself. Okay, that's a simple way of saying it. There's a few more complicated ways of going into this by looking at the graph of 2 to the minus t, but I'm not going to do that now. If you want to write it another way, you could say as t gets very large, i.e. as time in the future gets very big in terms of hours here, 1 over 2 to the t never reaches 0. Okay, it tends to 0, but never actually gets there. So you're always doing some small fraction of what you started with. So a reasonably complicated question there, I'd have to say. And if these are going to be how the questions are going to be in the next exam in 2017, then I would suggest you do quite a few of these, because they do seem a slightly different flavour than the last 7 or 8 years worth of exam papers, in my opinion. So let's have a look at the next question. Question 16. The graph of y equals f of x is transformed to give the graph of y equals negative f of x plus 3. And we're given a coordinate 9, 1, and that's the point A. And that's on the graph of y equals f of x. What we have to do is find the coordinates of the point P, and that's on the graph of the transformed graph the transformation, and that's y equals minus f of x plus 3. Now, I'm not going to go into massive detail here, but we've got two things going on here. Something inside the bracket, which is always to do with changing the x values, and then something outside the bracket, which is always to do with changing the y values. That's the easiest way to look at it. And I always start within the brackets first. So I look at the point 9, 1, the coordinate, and first of all I'll look at this transformation here. Now this is a translation of 3 units parallel to the x-axis, but which direction is it? Well, it's to the left. So we take our x value here, and all we do is we decrease it by 3. So that's now worth 6. We then look at this number here, and that's negative 1. And what that means is y is now minus what it was before. So we look at the y coordinate now, and all we do is we make that negative 1. What that actually has the effect of doing is, this was the translation we said here, and what this does here, this minus, is it makes y the negative of what it was before. So if you think of a graph here, and we have this as the x-axis and this is the y, it says that y becomes the negative of itself. So what that would actually do is mirror this graph here. So it's basically a mirror in the x-axis. Not to be confused with this one here. This is when x becomes its negative. So again, if we had a graph here, x and y, and we had some kind of thing going on here, something like this, then basically all these points would come to here, and all these points would go to there, and that would be a reflection in the y-axis. So there's the transform point, that's the coordinate p, 6, negative 1. Question 17. Quite a tricky question. You're given the perpendicular height of the cone as 16x units, and you're given the diameter of the base of the cone is 24x units. So straight away I think it'll be a good idea to put in the radius, which will just be 12x units. It says the curved surface area of the cone is 2160 pi, and we've got a formula here, and the curved surface area of a cone is equal to pi times the radius, which we have, times L. So what do we garner from that? Well, we can find out from this that L is just going to be 2160 pi divided by 12 pi x, i.e. this part here. Now we have calculators obviously, so we can see from here that we have half of this will be 1080 divided by 6. We could have a decimal on our calculator, but I'd just rather halve until we get down to a lowest form. So we get 540 over 3 of the x's, and then 3's into 54 is 18, so that must be L is 180 over x. So we've got that there. The next thing that I would do is I would look at a right angled triangle here, and I'd put this value for L in here, which is 180 over x, and I know this is 16x, and I think I'll just use Pythagoras to get the value of x. So let's see what happens there. And we'll have, by Pythagoras, 16x squared plus 12x all squared would be equal to 180 over x all squared. So we'd have 256x squared plus 144x squared is, well, 18 squared is 324, and then we'd have x squared here. And I think what I'll do next is I'll divide everything through by x squared. And then I would try and work out here how to get x on its own. So I'd have 256 and 144, which will be 3, that's 400, that's nice and easy. So 400 equals 324 lots of 100, so 32,400 over x to the power 4. And then from this, I would have x to the power 4 is 32,400 divided by 400. I don't need a calculator just yet because I can divide this through, cancel it down, and I can halve 324 to get 162, and then I can halve that again to get 81. And x to the power 4 is 81, means something times something times something times something is 81. Well, that something must be 3, because 3 squared is 9, and 3 squared squared is 3 to the 4, so that would be 81. So we know x is 3, so it's quite easy now. We can finish off the last part because we know the volume is going to be just popping these numbers into the formula. So we have 1/3 of pi times the radius squared. Well, don't forget the radius is 12x, 12 threes are 36, so that's 36 squared times the height, which is 16x, and 16 threes are 48. And all we have to do is, you can probably put all this into your calculator straight away. I'll do 3s into 48 is 16, so I'll have 36 squared times 16 times pi, and it wants the value of v, where v pi is the answer, so it just wants the value of 36 squared times 16, which I'm going to do on my calculator. So 36 squared times 16, and I get 20,736 pi. So the value of v here, where v is the integer, will be 20,736. So the main thing to remember with this question is that we put the radius in straight away. We looked at a situation where we used this formula here because we were given the curved surface area, so I used that. I then enabled myself to find an expression for L. I then simply used Pythagoras, and then from that I put in something here. Okay, I had a power of x to the 4, but that was fine because the numbers here and here were nice and easy, and if I had something to the power 4 is 81. At this point here you could have done 81 to the power a quarter, and that would have given you the 4th root. I'm sure there's another way of doing this question, and if you don't want to see it then you can skip ahead, because there's probably an easier way of doing it, because x to the power 4 is not too easy to use. So the alternative, and I'll do this in a different colour, you could have used Pythagoras straight away and said 16x squared plus 12x all squared square rooted would be L, and from that you'd get 256x squared plus 144x squared square rooted is L, so you just get 400x squared is L, square rooted that is, so L would be 20x, okay, and once you have that you can use this curved surface area part again and have 2,160 pi, which is in the question, would be equal to pi times the radius, which is 12x, times L, which is 20x, and of course then you can divide this both sides by pi, and then you've got on the left hand side 2,160, and then 12 times 20 is 240x squared. Divide both sides by 240, so you'd have 2,160 divided by 240 is x squared. So you can use a calculator, I don't really like using one too much. 12s into 108, well 9 12s are 108, so 9 is x squared, so x is 3. And then when you've got your x is 3, then you just do the last part again, just how we did it here before. So you just put the value of x in there as 3, and you can find your value of v. So that's probably the way that most people would approach it. They'd use the Pythagoras part first, but you don't have to. You can be really inventive. In fact, there's probably a way you can use similar triangles as well, perhaps, but I won't go into that right now. Question 18. Thelma spins a biased coin twice. The probability that it will come down heads both times is 0.09. Calculate the probability that it will come down tails both times. So it's a biased coin, so it's not 50-50. And the other thing to work out is that we have 0.09 as the probability for the coin landing twice on heads. So that means the probability of heads times the probability of heads is 0.09. So if we do the square root of 0.09, then we would have 0.3 multiplied by 0.3 would give us 0.09. So that means the probability of heads will be 0.3. So the probability of tails, as it was a biased coin, would be 0.7. So coming down twice on tails would be the probability of tails multiplied by the probability of tails, which is 0.7 times 0.7, which is just 0.49. Okay, so there's an assumption there that you know why to multiply with probability, and there's plenty of videos out there explaining that. I've got one in a playlist on probability if you want to have a look at it. Okay, so let's have a look at the next question. Question 19. We have to write this number 0.000423 in standard form. So let's write that number down first. Now, standard form is always a number between 1 and 10, not including 10, times a power of 10. So for example, if we thought that we had a decimal 0.4, that would be 4 divided by 10 once, i.e. times by 10 to the minus 1. If we had 0.003, that would be 3 divided by 10 twice, i.e. times 10 to the minus 2, and so on. Now, the best idea to look at this one is to think where the decimal point would be. So it would be at 4.23, and then you have to say to yourself, what would you have to do to 4.23 to get to this number? Well, you'd have to divide it by 10 how many times? Once, twice, 3 times, 4 times. And dividing by 10 is to the power minus. So we have minus 4. And if you think about it, 10 to the minus 4 is just 1 divided by 10 4 times, which is 1/10,000th, for example. And for those that don't like standard form too much, if you had a very large number, say like this, then you'd say to yourself, well, where would the decimal point be between 1 and 10? It would be 4.3567, and then how many times would you have to times by 10 to get back to the original number? Well, that is 1, 2, 3, 4, 5, 6, 7 times. So it's times 10 to the power, well, not negative this time, but positive because you're multiplying, and so on. Okay, so now we can look at part B, and that's 4.5 times 10 to the 4. Well, that's the same as writing 4.5 and multiplying it by 10 4 times. Okay, that's different from this, which would be taking the number 4.5 and dividing by 10 4 times. So that should be easy. So we'll times by 10 4 times, and we'd have 1, 2, 3, 4. So the answer would be, and we cross this out, it would be 45,000. and that would be it as an ordinary number. So I'm not going to be teaching standard form there. Again, there's plenty of videos on that. But if you've got a rough idea of standard form, it's just about timesing and dividing by 10 as many times as you can, really. That's the basis of it all. So let's have a look at another question. Question 20. Mark has a clay model. He will now make a clay statue that is mathematically similar to the clay model. The model has a base area of 6 centimetre squares, so we'll write that down here. That's the model, and that has 6 centimetre squares as an area. And then the statue will have a base area of 253.5 centimetre squares, so again an area. Now here's the thing, when we want to use the clay to make the model, we have 2 kilograms of clay which is used, and that's a volume. Okay, so when we're using the clay, we're looking at the volume here. Now I'm going to write that again, and it says clay is sold in 10 kilogram bags. Okay, so we'll come to that later. The first thing we need to look at is, in terms of an area, how much is the scale factor of enlargement in terms of area? Well, we can do that by doing 253.5 divided by 6. So we'll do that first. So 253.5 divided by 6, and that is 42.25. Now, this is our area scale factor. So if you remember about similarity, you've got length similarity, you have area and volume. Now, if we know that the scale factor for the area is 42.25, then to go to the length, we have to do the square root, because area is all about units squared, and length is all about units. So we need to square root the area factor to get the length factor of enlargement. So if we do the square root of 42.25, I'll do that now. So we'll do that to the power 0.5, and we get a nice answer here of 6.5 as the length scale factor. Now you can work your way up to the volume scale factor, because volume is in units by units by units, which is units cubed. So if we take this number here and we simply cube it, and we can do that on the calculator now, and I get a volume scale factor of 274.625, which seems a lot, but it's absolutely fine. So we take our 2 kilograms and we just multiply it by 274.625. So we times that by 2, and we have 549.25, and that will be kilograms needed to do the statue. Now it says clay is sold in 10 kilo bags, and it says how many bags of clay will Mark need to buy. Well, you just simply divide this number here by 10, and we get 54.925 bags, so he's going to have to get 55 bags. So on the surface that problem seems quite difficult, but if you just try and look at the way of getting from the area of the model to the area of the statue, once you've found that, you can always work back to the length. I always work back to the length, and then from the length you can get to the volume if required. If you're given the volume of the model and the volume of the statue, well, all you do is you take the volume number and you cube root it to get to the length, and then you square that number to get to the area. So whether you're given the area or the volume, you can always get back to the length and then get to either one of the other ones that you don't know. So there's always a way forward on these. So that's that question. Question 21. Show that the equation 3x squared minus x cubed plus 3 equals 0 can be rearranged to give this form that we've got here. Well, let's start with the initial form we have, which is a cubic. And one thing in maths is to think, well, what did we end up with here? We had a 3 on its own, so we've already got one of those, so we're going to leave that as it is. And then we have another 3 here, but comparing it to this one, it hasn't got the x squared term, so that gives us a clue to divide everything by x squared first. So if we divide this side by x squared and divide this side by x squared, we're going to get 3 minus x plus 3 over x squared equals 0. And then if you look at this negative x here, it's a positive x here, so if we add x to both sides, we're going to have 3 plus 3 over x squared equals x, and that's the same as x equals 3 plus 3 over x squared. There is another way of doing these, and it's a bit contentious because people think that it's cheating, and in some kind of ways it is. So I'm not trying to teach you bad ways here, but if you start from the actual answer and times both sides, say by x squared, and then you can take away x cubed from both sides. And then what you can do is you can switch the sides around and you'll end up with where you started. So all you'd have to do is put this here, and there you go. Now that's only if your algebra is really weak and you're really struggling. It's really up to you. This is the preferred way though. Let's look at this part B now. What does this form actually mean here? Well, what we have is we have an iterative form, because this x subscript n plus 1 means that if we want to find the next term of this iterative form, we have to start with some initial term, i.e. x subscript nth term. Now we're always given a starting value, and in this context we're given x subscript 0 equals 3.2. So we've got to find subsequent values, and I'll just stop saying subscript because it's annoying me. I'll say x1, x2 and x3. So let's have a look and see what this means here. So let's get rid of this here, so we can just see part of it. Now what I've actually done here is I've created a graph, and all I've done is I've graphed the left hand side here, x, y equals x, which you can see here. When you have an iterative form, you're always going to get x on one of the sides, so we're always comparing it to the line y equals x here, which I've done. And then I've just graphed the right hand side, which is 3 plus 3 over x squared, which I've got here. Okay. Now this part of it we're not going to look at because there's no intersection with the line y equals x, but on this part, the first quadrant here, there's something nice going on and there's a solution. So what I've done from there is I've basically zoomed in, and just so I make it really clear, this was my initial line y equals x, and this is a zoomed in part of this blue curve which was here. Okay, so I've zoomed in between 3.2 and 3.4. So it said let's start with x0 is 3.2. Well, what happens when you do that? Well, when you start with, say, a first value of 3.2, there's your line y equals x. So it's saying let x equal 3.2, and it will keep going until it hits the blue curve which we want to look at, i.e. the right hand side here. And you'll then get a value. Now what will that value be? Well, if you use your calculator and you look at this right hand side, 3 plus 3 over, well, you want x0 to be 3.2, so this n part here would be 0 and you'd have just 3.2 squared. So if you put that into your calculator, then you're going to get this, and it's rounded to 4 decimal places here on Desmos, so it's not going to be as accurate as your calculator display, but never mind. So this is what you've got, 3.2929 and so on. And how is that relevant to this graph? Well, if you think about it, you started at 3.2, I'll keep this in black, you started at 3.2, you read along to the blue curve, and then that was what this actually had as a value. Now, when you're graphing something on the left, like the line y equals x, and something on the right hand side, say 3 plus 3 over x squared, that's like saying y equals this and y equals that, and that's how you can graph them separately. So when you put x0 is 3.2 into this right hand side, that becomes a new y value. And then what that does is that searches for the line y equals x. And then you've probably guessed it, that becomes your next x value, i.e. x1. So we're then at this stage here, and then it just repeats. It looks for the blue curve, it finds it, and then that becomes the new y value. It then finds the graph y equals x, that becomes the new x value, and so on. And then what will happen is, and this term where it does this kind of shape is called cobwebbing, like a cobweb, a spider's cobweb. If it converges, i.e. gets towards a final solution, it will converge towards a nice root. Okay, so I'll write some of these words down here. So you've got cobweb, you've got converge, and you've got root. So basically, if you just want a method, then skip this part and we'll go straight to what you would just do in the exam. So if you had these values here, you would say in your calculator 3 plus 3 over 3.2 squared, and I'll do that quickly. So 3 plus 3 divided by 3.2 squared, and I get 3.29296875. So that becomes our x1 value. Then we put this value back into the right hand side again. So what you can do is you can just type in 3 plus 3 divided by ans squared, ans being your last thing you had in there, and you'd get 3.276659 and so on, and that would be your x2 value. And then you can just press equals on your calculator again. Instead of doing the whole thing, you just keep pressing equals, 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 and it will give you the next one, the next one, and the next one. That's if you have the ANS command on your calculator. If you don't, you just have to type the whole thing back in again. So you get 3.279420685, that will be x3. And if you just press your button a few more times, after about the 9th or 10th press, you get to something which is around 3.279 to 3 decimal places. Okay, so that's iteration, and it doesn't say to round these values, so I would just leave it as your calculator display. But when I explain this to you here, this is exactly what's happening, and it's all about the line y equals x and what you've got on the other hand side of your equation. So if you've got x on the left hand side, whatever you have on the right hand side, if it's nice, i.e. it converges, you'll get a nice root. If it's not nice and you choose a form that doesn't work, it will diverge, which will mean that this won't have such a nice pattern to it. It might do the opposite and actually diverge away from the thing you want. Okay, so this is probably why in this particular question, I'll get rid of all this rubbish here. This is why it gave you this iterative form, because the examiner knows that this one actually works. So it says in the next part, part C, it says explain what the values of x1, x2 and x3 represent. And what I've said here is x1, x2 and x3 are just better approximations for one of the roots of the initial cubic. Don't forget that initial cubic that we had to start with. So that's what iteration is, and if we come across that again, I'll explain it again. I probably went into a bit more depth than what you needed, because I'm sure you've been taught really well at school by your teacher on this anyway. But if you've got a cover teacher or something, and maybe you're not going to school for some reasons, then hopefully this will give you a heads up on it. Question 22. Here are the first 5 terms of an arithmetic sequence, and we have to prove that the difference between the squares of any 2 terms of the sequence is always a multiple of 24. Now, just looking at this, if I didn't have the experience of this type of question, I would probably start messing around with the actual numbers themselves and then just squaring them, taking them away from each other and seeing if it's a multiple of 24. But you've got to do any 2 terms of the sequence. So I think what we should do first is try and find the nth term. Then we can work in general terms for any 2 terms of the sequence. So first thing to look at is that the differences are 6. The first differences, so it's definitely linear, and it says it's arithmetic, which means it goes up or down by a given number. So we know it's in the 6 times table, so if we write the 6 times table underneath, we can see that we always have to add 1 to the 6 times table. So 6n plus 1 will be the nth term. Okay, that stands for nth. So if we look at the nth term and the next term, say for example, so we just have to add 6, we'd have 6n plus 7. Then why don't we look at these 2? Because they represent any 2 terms in the sequence where n can be anything we like. So we shall square them first. So let's get a little bit more room here. So I'm going to square this one first. So 6n plus 7 squared, and then I'm going to take this one squared away from it. So what have we got? We've got 36n squared plus, well, 7 6s are 42 doubled is 84n plus 49. You can do this in a grid if you are not as experienced at this, and you'd get the same answer. And then we take away, and I'm doing a square bracket here, and then I'm going to have 36n squared. That's 6n doubled is 12n plus 1. And let's see what we've got here. Well, we're going to have 36n squared minus 36n squared, which is 0. We're going to have 84n minus, that should be 12n here, sorry, minus 12n. And then we've got 49 minus 1, which is 48. So let's have a look at what we've got so far. We've got 84 minus 12 in terms of n, that would be 72n plus 48, and it looks as though we can take 24 out as a factor and have 3n plus 2. So what that means is we've got 24 lots of something dependent on what n is. So it doesn't really matter what we say n is, because if we say for example n is 100, then we'd have 302, but we've got to times it by 24, so it's going to be in the 24 times table, i.e. a multiple of 24. So that's how I would approach that particular question. And I would definitely write a little sentence here, which I'm not going to do now, saying there's a factor of 24, so it's a multiple of 24, i.e. in the 24 times table.